Welcome to this NPTEL course on Dynamics and Control of Mechanical Systems. My name is Ashitava Ghoshal. I am a professor in the Department of Mechanical Engineering, also in the Center for Product Design and Manufacturing, and in the Robert Bosch Center for Cyber-Physical Systems, Indian Institute of Science, Bangalore. In the last week, we had looked at position and orientation of a rigid body and combined motion of a rigid body consisting of translation and rotation. In this week, we will look at the velocity and acceleration of rigid body in 3D space. There will be two lectures in this week. The first lecture will be on linear and angular velocity of a rigid body, and the second lecture would be the general motion of a rigid body and also particles, where we look at the velocity and accelerations of the rigid body and the particles on a rigid body. So the first lecture is on linear and angular velocity of a rigid body in 3D space. So just to recapitulate, in last week we had looked at a right-handed coordinate system. So basically any coordinate system will have an x-axis, a y-axis and a z-axis and an origin. The axes are unit vectors x hat, y hat and z hat. A rigid body in 3D space is specified by 6 quantities with respect to a reference coordinate system. So they could be Cartesian coordinates x, y, z of a point on the rigid body. The orientation of the rigid body can be represented in several ways. It always has 3 independent parameters, and so we had looked at rotation matrices, angle axis form, Euler parameters, Euler angles and so on, and we developed algorithms to convert from one representation to the other. And we finally looked at position and orientation of a rigid body as a 4x4 transformation matrix, where some part of this 4x4 matrix contained rotations of the rigid body and one column, last column, contained the translation of the rigid body. So I showed you that the general rigid body motion in 3D space can be thought of as a rotation about and along a line in 3D space. In this week, we will look at rate of change of position and orientation with time. So first let us look at the linear velocity of a rigid body. So this figure here shows the rigid body in 3D space, this odd shaped thing, and I have shown you a coordinate system which is x, y and z, and this is the origin of the coordinate system. There is also another coordinate system which is attached to this rigid body, and it is shown at 2 instants. So this coordinate system is labeled as I. So, and this is at I at t plus delta t. So as you can see that the x, y and z axis are translated in a parallel manner. So if this were the x-axis, this is the x-axis, both are parallel to each other. Likewise the y and the z-axis. The origin of the ith coordinate system is currently here, and it goes to some other place. So this is OI and this is also OI, but at t plus delta t. So as I said, this is the rigid body at t, and this is the rigid body at t plus delta t. So the linear velocity of OI, which is the point of interest, basically the origin of the coordinate system which is fixed to the rigid body, it can be defined using very basic notions of calculus. So we see that the vector OI at t plus delta t is subtract OI at t, then divided by delta t, and as the limit of delta t goes to 0, we get the velocity of this origin of the coordinate system. It can be also denoted as d by dt of OI of t. Okay, So this is very, very basic calculus. So the 0 here denotes the coordinate system, which is the reference coordinate system where the limit is taken. So remember, if you have two vectors and you are subtracting these two vectors, both of them have to be in the same coordinate system. Otherwise, it doesn't make sense. So this vector OI of t and OI of t plus delta t are with respect to the 0 coordinate system, the reference coordinate system. So the linear velocity vector can also be described in some other coordinate system. So for example, if there was a j coordinate system, some other coordinate system, let's say j, and I want to describe this linear velocity vector in that j coordinate system, so then what we can denote that vector in this 0 v 0 I, but with respect to a j, and what it means mathematically is that we pre-multiply this linear velocity vector with a rotation matrix which is J0R. Okay, so basically 0 with respect to the j coordinate system. Okay, and again, if you go back and remember what we did with rotation matrices, if you multiply these two, basically we transform it to another coordinate system, which in this case is the j coordinate system. So any linear velocity vector of a rigid body or a point on the rigid body can be associated with two different coordinate systems. Okay, this is a very useful thing to recognize and also very basic, and it's also very we'll see later on that it should not cause any confusion. So the two different coordinate systems are one in which the difference is taken or in which the derivative is taken, and the other one is the coordinate system in which this velocity vector is described. Let's continue and look at the angular velocity of a rigid body in 3D space. First thing to remember is angular velocity cannot be described as a time derivative of three quantities, let's say three Euler angles. Okay, so we can represent the orientation of a rigid body using three Euler angles, let's say theta 1, theta 2, theta 3. We cannot describe the angular velocity of this rigid body only in terms of theta 1 dot, theta 2 dot and theta 3 dot. This is unlike the position velocity relationship. So if the position vector is x, y, z, the linear velocity is x dot, y dot, z dot. So angular velocity will be obtained from the time derivative of a rotation matrix. Okay, so let's recall, if you have a rotation matrix 0 IR, and if I post multiply this rotation matrix by the transpose of that same matrix, we get the identity matrix. So this is same as saying that the inverse is same as the transpose. So if you have A into A inverse, two matrices, we'll get identity. In our case, the rotation matrix inverse is same as the transpose, so hence we get this. Okay, so I coordinate system with respect to some reference coordinate system 0 in rotation matrix 0 IR, and 0 IR transpose is its multiplication, we'll get the identity matrix. If we differentiate this relationship with respect to time, so basically we have to use chain rule. So you can see that the first term is so R dot into R transpose, and the second term will be R into R dot and the whole of transpose. So the right hand side is identity, so the derivative of that is 0. We can recall that the derivative of a matrix implies the derivative of all the components of the matrix. So if you remember, R contains R11, R12, R22 and with 9 elements, 9 Rij's. So R dot means the time derivative of each one of those 9 elements in the matrix. The above equation here, which is R dot R transpose plus r into r dot transpose equal to 0 can be rewritten in this form. So basically first term is the same, but the second term is we are using the fact that A into B whole transpose is B transpose A transpose. So I am going to rewrite this as r dot r transpose, again the whole transpose. So r transpose r of the transpose of that will give me r, and then this is 0 I r dot transpose, and the right hand side is 0. So now you can see that this total quantity, which is r dot r transpose, is a skew-symmetric matrix. Okay, in linear algebra, a skew-symmetric matrix is one in which A plus A transpose is 0. Okay, in the first module, we had looked at what is a skew-symmetric matrix, where the diagonal elements are 0 and the off-diagonal elements are arranged in a particular form. And this is also another way of saying that this, if you have a matrix A, any matrix, and then A plus A transpose is 0, then A is a skew-symmetric matrix. So we are going to denote this r dot r transpose using this matrix omega. We will continue to keep 0 and I because this is the skew-symmetric matrix I with respect to 0, and this R here shows that we are starting from this kind of relationship, which is R into R transpose is identity. Okay, very soon we will see that we could also have started with R transpose into R, which is identity, then we would have got some other matrix. So I have a skew-symmetric matrix which I will call 0 I capital omega, and with a subscript R, which is nothing but R dot R transpose. So let's continue. So I'm going to show you that the angular velocity of a rigid body and the skew-symmetric matrix are intimately related. So the skew-symmetric matrix 0 I capital omega R can be written in this general form of any skew-symmetric matrix, which is the diagonal elements are 0. So this is that minus z component, this is y component, this is minus omega x, this is by skew-symmetric property, this should be plus omega z s, and this is minus omega y s, and this is plus omega x s. So we will see later this s, it has some significance, but it doesn't matter right now. So we will come to what is s little while from now on. So the product of this skew-symmetric matrix 0 I r into any vector, as has been mentioned earlier, and one can verify, this product is nothing but the cross product of this vector, which is omega 0 I omega s into 0 p. So we are going to use this notation. So 0 here means the reference coordinate system, I means this is the ith rigid body, s here we'll see stands for some space fixed angular velocity vector, and 0 p means this is a position of a point with respect to the 0 coordinate system. Okay, so important thing here is the skew-symmetric matrix into some px, py, pz. If you expand it, you will get this, which is exactly the same as this cross product of two vectors, angular velocity vector and 0 p. So this quantity here is called the angular velocity of rigid body I with respect to the 0 coordinate system. Okay, so the matrix, skew-symmetric matrix, is also sometimes called as the angular velocity matrix, whereas this vector, which is, there are three components in the skew-symmetric matrix, which is omega x, omega y, omega z, that is called as the angular velocity vector of I with respect to 0. So important thing to realize is that in contrast to the linear velocity vector, the angular velocity vector is not so straightforward. Linear velocity vector x, y, z is the position of a point on the rigid body, we just take the derivative of that position vector, which is x dot, y dot and z dot, and that is the linear velocity. In the case of angular velocity, we have to go through this skew-symmetric matrix, which is nothing but r dot r transpose. So it's a little bit more complicated. So let us continue, and we find the angular velocity vector in terms of Euler angles. So we recall that the rotation matrix of a rigid body in terms of Euler angles can be given in variety of ways. So if you have x, y, z Euler angles, and the rotation about x is theta 1, rotation about y is theta 2, rotation about z is theta 3, then the rotation matrix 0, I, r can be written in terms of cos and sine of these three angles. Okay, so we had discussed these Euler angles. These are called x, y, z Euler angles because they are rotations about x axis, y axis and z axis. And we can see that you will get terms like cos theta 2, cos theta 3, sin theta 2, cos theta 1, cos theta 2 and so on. So it is a reasonably complicated expressions of cos and sine of theta 1, theta 2 and theta 3. Okay, we had done this in the first week. If you have forgotten, please go back and refresh. We can now obtain r dot r transpose of this matrix. Okay, so what is the r11 dot? We have to again use chain rule. So cos theta 2 will be minus sin theta 2 into cos theta 3 plus cos theta 2 into minus sin theta 3. The first term should have theta 2 dot, second term should have theta 3 dot. So the derivative of S2 is cosine theta 2 into theta 2 dot. So remember, when you take the derivative, you have to use chain rule, and also you have to introduce theta 1 dot, theta 2 dot and theta 3 dot. So the x, y, z components of the angular velocity vector can be obtained from this skew-symmetric matrix, and they look like this. So the x component will have theta 1 dot plus theta 3 dot into sine theta 2. Y component is given by theta 2 dot into cos theta 1 minus theta 3 dot into sine theta 1 cos theta 2, and the z component is theta 2 dot sine theta 1 plus theta 3 dot cos theta 1 cos theta 2. Okay, so I have skipped a few steps, but this is very straightforward and routine. You have to take element by element derivative. So r11 dot, r12 dot, r13 dot and so on, and use chain rule and introduce theta 1 dot, theta 2 dot and theta 3 dot. We will be left with also sine theta 2, cos theta 1 and so on. Okay, and then you multiply by r transpose, and then you will get a skew-symmetric matrix, and you take out those terms which are the x component, y component and z component. So this is the way to obtain the angular velocity vector if you are given the x, y, z Euler angles. X, y, z means if you are given theta 1, theta 2 and theta 3, which are rotations about x, y and z Euler angles axis. So let us continue. If you want to find the angular velocity in terms of some other Euler angles, remember, Euler angles could be about three distinct axes, which I showed you. Last one was about x, y and z. You can also have about two distinct axes, which is, let's say, z, y and z. And again, let's assume that rotation about first z is theta 1, rotation about y is theta 2, rotation about the last z is theta 3. Again, we can find the rotation matrix, which is nothing but rotations about z, y and again z, multiply in that order, simplify, and you will get a rotation matrix which looks like this. So here the term, so R33 is C2, okay, R13 is C1 S2. Again, C1 means cos theta 1, S2 means sin theta 2, and so on. So S3 means sin theta 3. So we can find this rotation matrix. This was done again last week, so please go back and refresh if you have forgotten. Again, we can obtain this R dot and R transpose. R dot again means exactly the same thing. So for example, what is R33 dot? It is minus sin theta 2 into theta 2 dot, and we have to use chain rule for all others. So as you can see, you will have many terms. So C1, C2, C3, so you have to use chain rule, and you will get theta 1 dot, then you will get theta 2 dot, and you will have theta 3 dot, and so on. Okay, and then you post multiply by R transpose, this R dot matrix, and again we can extract the x, y, and z components of the angular velocity vector. The x component in this case is given by theta 3 dot into C1 S2 minus theta 2 dot into S1, and y component is theta 3 dot into sin theta 1 into sin theta 2 plus theta 2 dot into cos theta 1, and the z component is theta 3 dot into cos theta 2 plus theta 1 dot. So as you can see, the x, y, and z components of the angular velocity vector is different, and that is because we are using a different way of representing orientation. So previously it was XYZ Euler angles, now we have ZYZ Euler angles, and naturally the rotation matrices were different, so the angular velocity vector would also be different. So let's continue. So there are two kinds of angular velocity vectors. One is called space fixed and one is called body fixed. So I showed you what is 0I omega r, and this r was derived from multiplying this rotation matrix to the right. So this is like A into A transpose is identity, or A into A inverse is identity. This is called right multiplication, and that is where this capital R comes from. This denotes the angular velocity obtained by multiplying the rotation matrix to the right. And the angular velocity vector which we obtained from R dot R transpose is 0 omega I s. So this s here stands for space fixed angular velocity. So this superscript s is from this right multiplication, then the time derivative, and then R dot R transpose, and whatever the angular velocity vector we extract from the skew-symmetric matrix, this is called space fixed angular velocity. Okay, we will see later that there is a nice interpretation of space fixed as, and what will come right now. Another way to derive a skew-symmetric matrix is to look at this pre-multiplication. So I have a rotation matrix. I can pre-multiply by R transpose, and again I will get identity. Okay. So again, if I take the dot product, if I take the time derivative of this matrix into this matrix, I will get another skew-symmetric matrix. Okay. If you think about it, it is not very hard. Okay, so this is called as the left multiplication because we are pre-multiplying the rotation matrix to the left, and the skew-symmetric matrix that we will get from left multiplication and taking the time derivative of this equation is called 0I omega L. Okay, and that will be defined as 0I R transpose into 0I R dot. So as you can see, this can be remembered as R transpose R dot. Previous one was R dot R transpose. Now, so this is like product of two matrices, but the order is reversed. And we know matrix A into B is almost never the same as B into A. So the skew-symmetric matrix that we will get this way, which is R transpose R dot, is with a B superscript. So again, we will have 0 in the diagonal terms. We will have minus omega z with a B superscript omega yb minus omega xb and so on. So we can again find a new skew-symmetric matrix which will be different from the previous one, because remember the previous one was r dot r transpose, now it is r transpose r dot. Okay, so we want to distinguish between these two angular velocity matrices, which is one was 0I omega L and the previous one was 0I omega R. So 0I omega L is derived from the left multiplication R transpose R, which is identity. And the angular velocity vector which you obtain from the skew-symmetric matrix from left multiplication, they will be denoted as omega xb, omega yb, omega zb. Previous one there was a superscript of s, now there is a superscript of b, just to distinguish the two ways which we derive the angular velocity vector. So let us continue with the angular velocity vector. So as I said, we have an angular velocity vector with the superscript b. This is called the body fixed angular velocity vector of I with respect to 0. Okay, so this came from the left multiplication, and the skew-symmetric matrix which was obtained from R transpose R. So let's take an example. If you look at the angular velocity vector obtained from R transpose R, and let's look at the ZYZ Euler angles, then the omega x b is minus theta 1 dot s2 c3 plus theta 2 dot s3. Omega y component is theta 1 dot s2 s3 theta 2 dot c3, and the z component is theta 1 dot into cos theta 2 plus theta 3 dot. Okay, so as you can see, the space fixed angular velocity vector again for ZYZ Euler angles, this was obtained from R into R transpose is identity. Okay, so the x component of the space fixed is theta 3 dot into C1 S2 minus theta 2 dot S1. Omega y is theta 3 dot into S1 S2 plus theta 2 dot C1, and omega z is theta 3 dot C2 plus theta 1 dot. So as you can see, they are very, very different. Okay, so you need to be careful to understand which angular velocity vector you are talking about, and we can go back and realize that one was obtained from left multiplication and one was obtained from the right multiplication. It turns out that these two skew-symmetric matrices, which is the left one and the right one, are related like two tensors. So basically, if you have a matrix, a tensor in one coordinate system and a tensor in the other coordinate system, so you can relate the right one as R into left into R transpose. So this is similar to many other tensors which you might have seen in undergraduate. So for example, the stress tensor, or for example the inertia matrix, they transform according to these rules, and the angular velocity matrices also transform according to this rule of tensors. And the angular velocity vector also can be written as omega is same as 0I rotation matrix into 0 omega ib. So basically what is happening is that we have this angular velocity vector which is with a b superscript is related to the angular velocity vector with an s superscript by means of this rotation matrix. Okay, so this will come in handy later on. The rotation matrix for this example, just for recapitulation, is shown here. So it has this C2 here, C1 S2 here, S1 S2 here, and so on. So if I take this rotation matrix and put it here and then pre-multiply 0 omega IB with this rotation matrix, I will get 0 omega I S. Okay, so x component y and z of the space fixed angular velocity vector is related to the rotation matrix times the x, y, z angular velocity vector of the body fixed. To get a little bit of more insight into these two different kinds of angular velocity vector, the space fixed and the body fixed, let us look at this figure. This figure shows a rigid body. Okay, this is a rigid body at time t, and this is the rigid body at time t plus delta t. We are only interested in the rotation. So what we will see or look at is this rotation with one point fixed. So the origin of the two coordinate systems x, y, z at 0 and x, y, z at some t and t plus delta t, all of them are not changing. So 0 is the reference coordinate system. The rigid body at t is given by I at t, and the rigid body at I at t plus delta t is given by another coordinate system. Okay, so this is a case, or this in mechanics we say it's a rigid body undergoing pure rotation about a fixed point. So one point in the rigid body is fixed and it is not translating. So the points OI at t and OI t plus t delta t are coincident, and only the elements of the rotation matrix are changed with time. A point P can be located in the rigid body I by means of this vector. So we will be using this vector, which is I up with a superscript I and a vector P. Okay, so again the same picture. So the location of this point P in the ith coordinate system, okay, is given by this vector. The same vector can be written in the 0 coordinate system or the reference fixed coordinate system as 0p is given by 0ir into ip. Again, it's very straightforward transformation of this position vector into the 0 coordinates frames. So since p is fixed in I, the derivative of this 0pi is same as 0pi, and then we can write this as 0ir dot into ip. Okay, so I am using the chain rule. So derivative of the right hand side should have one term which is 0ir dot into ip plus 0ir into ip d by dt of ip, but p is fixed in I, so d by dt of ip will be 0, so hence we get this expression. So now we are going to do a little bit of linear algebra and also a little bit of manipulation. So we know that the inverse is same as the transpose. Okay, inverse of a rotation matrix is same as the transpose. So what we can do is we multiply this right hand side. So this is r dot into ip. So that can be written as r dot into 0ir transpose 0p, because remember ip will be same as 0ir transpose 0p. Okay, so transpose can be same as thought of as inverse. So now let us look at this term. So if you take a look at this term, this is r dot r transpose. So this is the skew symmetric matrix coming from the right multiplication, which is 0I omega r, and we are left with 0p. So the linear velocity of this point in the 0 coordinate system can be written as omega is cross 0p. Okay, so it is very similar to what we have learned in undergraduate, that the linear velocity of a point which is rotating about this is like r cross omega, okay, or omega cross r, okay, correct, omega cross r. So we have this expression here for the linear velocity of this point which is rotating with one end fixed. So if you look at this expression once more, so other than the coordinate system I, which is denoting that we are interested in the rigid body I, everywhere we have 0 here. This is 0 here, this is 0 here. So the coordinate system I does not appear except in denoting the rigid body I, that we are interested in the rigid body I. Okay, so this is important, that the linear velocity of a point which is in a rigid body which is rotating with one point fixed is like omega cross r, and that omega is the space fixed angular velocity vector. So since I is not appearing anywhere in this expression except to denote that we are interested in the rigid body I, everything is with respect to 0, 0 and 0 here. So the space fixed angular velocity vector is said to be independent of the choice of the body coordinate system. Okay, so let's go over this a little bit. So it does not really matter what is the body coordinate system, because we are doing omega cross r, and this omega is the space fixed angular velocity vector. Let's continue. We again have this rigid body. There's a fixed or a reference coordinate system. There is a ith coordinate system attached to the rigid body at time t, and then this coordinate system goes to t at t plus delta t. Okay, this is the I at t plus delta t. So now if you use the relationship between omega r and capital omega L, which is, remember, it was transforming like a tensor. So I can write the linear velocity of this point with respect to the 0 coordinate system as 0IR, 0IL, 0IR transpose, 0P. Because remember, this is the omega s, space fixed angular velocity vector, and the matrix associated with the space fixed angular velocity vector was r here, but then I am writing r as r omega r transpose. Okay, so let's continue. Now this part here can be written as IP. Okay, so remember, this is r inverse 0p. So this is a vector now transformed to the ith coordinate system. So we have one omega L here and rotation matrix, and I, the point in the ith coordinate system. Now we can pre-multiply both sides of this and this with 0IR inverse. Okay, so 0IR inverse into 0VP will be left with 0I omega L into IP. Okay, so R into R inverse is identity. So if you do this, this quantity here, if you think a little bit, is the linear velocity of the point P expressed in the ith coordinate system. So 0IR inverse into 0BP is the same as I0 into 0VP. So this again 0 0 will cancel out and we will be left with IVP. And this is equal to the left angular velocity matrix into IP. So remember, this is a skew-symmetric matrix. So this is nothing but the body fixed angular velocity vector cross IP. So we have this point P in the ith coordinate system with respect to the ith coordinate system. If you pre-multiply by the angular velocity vector b with a superscript b, I will get the linear velocity of the point P in described with respect to the ith coordinate system. Okay, so again, if you think a little bit, except for the fact that the 0 is showing you that we are discussing a fixed reference coordinate system, it doesn't appear anywhere else. Okay, so the body fixed angular velocity vector is said to be independent of the choice of the fixed coordinate system. Okay, this is reason why one is called body fixed, because it doesn't matter what is the choice of the reference coordinate system or the zero coordinate system. In the case of space fixed, it doesn't depend on what is the choice of the coordinate system attached to the body. So unless specified, most of the time we will be using space fixed angular velocity vector. And just to recollect, the space fixed angular velocity vector is derived from r dot r transpose. Okay, let's go back and see how we can look at this angular velocity vector in terms of some other representation of orientation. So one of the representation of orientation was this Euler parameters, and if you recall, the Euler parameters consisted of 4 parameters. They are basically the axis about k, which is kx, ky, kz. It's a unit vector, and then there is this angle, which is the rotation about that axis. And the Euler parameters, 3 of them were nothing but this k vector into sine phi by 2. So this is a vector. And the 4th parameter was the scalar, which is epsilon 0, which is cos phi by 2. And there is a constraint. So there are 3 parameters here, epsilon 1, epsilon 2, epsilon 3, and there's a 4th one, epsilon 0. And the constraint is epsilon 0 square plus epsilon 1 square plus epsilon 2 square plus epsilon 3 square is 1. So for phi equals pi, okay, or epsilon 0 is 0. So cos of pi is pi by 2, because phi is pi, so this becomes pi by 2. Cos of pi by 2 is 0. So but epsilon I square is given by this 1 plus rii, okay, r11 plus r22 and r33. Okay, so they were the diagonal terms in the rotation matrix. So what it means is, even though phi is pi, so cos phi by 2 is 0, all the Euler parameters are non-zero. So there is no singularity in Euler, as in Euler angles. Okay, singularity means that I cannot determine all the Euler parameters. In the case of Euler angles, if there was a singularity, we saw that we could only do theta 1 plus minus theta 3. So 2 of the angles cannot be determined uniquely. So we chose theta 1 as something and theta 3 was 0. So please go back and refresh the algorithm to determine Euler angles given some rotation matrix. So for certain values of theta 2, we saw that it was singular. In the case of Euler parameters, singularity does not happen, because not all the epsilon i's become 0. So let us see if we can derive the angular velocity in terms of the Euler parameters. So it turns out that for Euler parameters epsilon 0, epsilon 1, epsilon 2 and epsilon 3, the rotation matrix is given by this. Again, this was derived. This is just to recapitulate. So the R11 term is this epsilon 0 square plus epsilon 1 square minus epsilon 2 square minus epsilon 3 square and so on. Okay, so these are some terms which we obtained from what is k and phi, and then k and phi was related to rij's. Okay, we can now obtain r dot r transpose. This is the space fixed angular velocity vector, and we can take the derivative of each one of these terms, epsilon. So the derivative of first one will be 2 epsilon 0 dot, and so on. We have to use the chain rule. And if you take those derivatives and reorganize, and you can see that the space fixed angular velocity vector is given in this form. So it is 2 into minus epsilon 0 dot into epsilon 1 plus epsilon 1 dot into epsilon 0 minus epsilon 2 dot epsilon 3 plus epsilon 3 dot epsilon 2. Okay, so this comes from applying chain rule, multiplying taking the derivatives and reorganizing. So 2 will come out. This can further be written, all this vector with 3 element, column vector can be written as a matrix. So this is a 3 by 4 matrix into 4 by 1 vector derivative of epsilon 0, epsilon 1, epsilon 2 and epsilon 3. So the space fixed angular velocity vector, which is nice to see that it can be obtained as epsilon 0, epsilon 1, epsilon 2 in some matrix into the time derivative of those 4 Euler parameters. Okay, so note this is not a square matrix. So this is not a 4 by 4 into 4 by 1. This is a 3 by 4 into 4 by 1. Why? Because the angular velocity vector is a 3 by 1 vector. It has 3 elements. We can also obtain the reverse. So we can also show that the angular velocity vector, if it is given 0 I omega I t, I can obtain the time derivatives of epsilon 0, epsilon 1, epsilon 2, epsilon 3 and epsilon and so on. So this is a 4 by 1 vector of time derivative of the Euler parameters. It is given as half into E of t transpose into 0 omega I. So these two expressions tell you that if I give you the rate of change of the Euler parameters, I can find the angular velocity. If you give me the angular velocity, I can find the rate of change of the Euler parameters. Okay, so there is no inverse going on because this E matrix is a 3 by 4 matrix. Okay, so E matrix from the previous slide is a 3 by 4 matrix, so inverse is not possible, but we don't need to obtain the inverse. Okay, in one case you have 2 ET, another case it is half E T transpose. Okay, so it's a very nice way of showing how the Euler parameters and their time derivatives are related to the angular velocity vector. So let's continue and look at some numerical examples, and these numbers are chosen arbitrarily just to show that we can calculate numerically the linear velocity, the angular velocity and also various other quantities. So if the position vector in the A coordinate system as a function of time is chosen arbitrarily as 4t cube plus 8t square minus 2t plus 5, this is the x component. Y component is 9t square minus t minus 6. The z component is 7t cube plus 10. So the derivative of this will give you the linear velocity. So this is d by dt of this vector will give you the linear velocity of the point. And just by very simple calculus, we can show that the linear velocity is given by 12t square, okay, plus 16t minus 2 and so on. So this is 18t minus 1 and this is 21t square. Okay, so if you want to evaluate the linear velocity at any time, so let's say at t equals 2, you can just substitute t equals 2 and we'll get these numbers. Okay, the basic idea here is that if you give me the position vector as a function of time, I can find out the linear velocity very easily just by taking derivatives of each of the components. Whereas if you want to find the angular velocity vector, then we cannot take simply the derivative of the components. okay, of theta 1 dot, theta 2 dot, theta 3 dot. Okay, so for example, in the ZYZ space fixed Euler angles, if I take the derivatives, I will get this, and the omega s is given by these functions of theta 3 dot, cos theta 1, sin theta 2, and so on. And if I choose theta 1 as 5t square minus 4, again chosen arbitrarily, theta 2 as minus 10t, any function of time, you have to substitute back all these things here to find out what is the angular velocity vector. So at t equals 3, we find out what is theta 1, then we find out what is theta 1 dot. How do I find out theta 1 dot? We have to take the derivative of this. So this will be 10t. Okay, and then substitute back all of this back here to get the space fixed angular velocity at t equals 3 given by this. So the basic idea here is to show that the angular velocity is a much more complex thing. It is not very simply the time derivative of the position vector. We can also find omega b with the superscript b. For ZYZ, the angular velocity with superscript b is given by minus theta 1 dot, sin theta 2, cos theta 3, theta 2 dot, sin theta 3, and so on. The z component is theta 1 dot, cos theta 2 plus theta 3 dot. This has been derived earlier. And then we can substitute again the same theta 1 as a function of time, theta 2 as a function of time, theta 3 as a function of time, and we can substitute back theta 1, theta 2, theta 3 here, and theta 1 dot, theta 2 dot, theta 3 dot here. And again for t equals 3, we see that the angular velocity vector has completely different components. Okay, so I wanted to show you that if you choose the body fixed angular velocity vector with the superscript b, then it is very much different from the space fixed angular velocity vector with the superscript s. Okay, and then you can also find the rotation matrix, and if you multiply r transpose into omega s, you will get back this omega b. In the previous slide, I had showed you what is omega s. Okay, and in a slide before that, I showed you omega s is r into omega b. So if you go back and compute omega b and omega s using these formulas and then do this matrix multiplication before r transpose omega s, you will get omega b. Okay, just to tell you that numerically also it matches with whatever we have derived the analytical expressions for omega s and omega b. The same thing we can show with Euler parameters. So if the k is given by 1, 2, 3 square root of 14, so basically it's a unit vector, and this phi is some again randomly chosen minus 9t cube plus 5t square minus t. I can find out what is the Euler parameters. Okay, so epsilon 1, epsilon 2, epsilon 3, the vector part is given by this expression, and epsilon 0 is cosine of this. Okay, so k, and this is sine phi by 2, and epsilon 0 is cos phi by 2. Epsilon dot, I can take the time derivative of this and obtain this. Epsilon 0 dot is given by this, and from the previous slide we know omega s is some matrix 3 by 4 matrix of all the 4 Euler parameters into epsilon dot, 0 dot, epsilon 1 dot, epsilon 2 dot, epsilon 3 dot. And the angular velocity for this example, this numerically chosen k and phi, is given by 0.522, 1.040 and 1.566. Okay, so this is a space fixed angular velocity vector for k and phi chosen randomly. So the next question which is of interest is, suppose you are given position So you are given velocities, both linear and angular velocities. Can we obtain the position and orientation of a rigid body? So clearly we have to numerically integrate the velocities, because integration of velocities will give the position vector. Similarly, somehow integration of the angular velocity will give you the orientation. So position is very straightforward. We have, say, v, which is the linear velocity, which is nothing but x dot, y dot, z dot. So we can just integrate, and with initial conditions, so position is very straightforward. Orientation from angular velocity is slightly more complex. Why? Because we have coupled nonlinear differential equations which relate the angular velocity and the three Euler angles. Okay. So as an example, if you remember, for XYZ Euler angles, the angular velocity x component is theta 1 dot into theta 3 dot into sine theta 2. The y component is theta 2 dot cos theta 1 minus theta 3 dot sine theta 1 cos theta 2, and the z component is theta 2 dot sine theta 1 theta 3 dot cos theta 1 cos theta 2. So what is the problem? We are given the left hand side. So I am given, let's say, some 1 radian per second here, 0.2 radians per second here, and let's say minus 0.03 radians per second as the z component. The goal is to find out theta 1, theta 2, theta 3, which are the XYZ Euler angles. So in order to find out theta 1, theta 2, theta 3, given the left hand side, I have to integrate these three equations. And as you can see, these three equations are coupled and nonlinear. Okay, so we need to go and use some MATLAB or some other tool to integrate. So again, let's take some simple numerical examples. So the linear velocity is given as cos t, sin t, and this minus 2 into t cube minus 15t minus 60 into 10 minus 3 meters per second. So this is the x component, this is y component, and this is the z component. So again, randomly chosen. So how do I find the position of the rigid body? If the linear velocity of the point is given, you just integrate. Okay, and if you integrate, you can see integration of cos t is sin t plus some constant, sin t is minus cos t plus some constant, and integration of this is given by this. Okay, so these xc, yc, zc are the integration constants. So if I assume that its initial conditions are 0, then we can obtain the position vector given this velocity vector. Okay, and this is shown in the adjacent figure. So I can integrate this and I can plot the position x, y, and z. X is the red line, y is the green line, z is the blue line, and with time I can plot these expressions. So this is sin t. You can recognize, no, that x is sin t, so the red line looks like a sin t. The green line is minus cos t, so it looks like this, whereas the z component is some complicated or polynomial in t. So let us continue. I want to find the angular velocity. I am given the angular velocity vector. I want to find the x, y, z Euler rotations. So I want to find out theta 1, theta 2, theta 3, which are the rotations about x, y, and z. Okay, so once I know theta 1, theta 2, theta 3, body fixed Euler rotations, I can find the rotation matrix x for theta 1, y for theta 2, z for theta 3, multiply the matrices in that order, and I can get back the rotation direction cosines and the rotation matrix. So as an example, let's assume that the space fixed angular velocity vector is given as 1, 2, 3. Okay, so it's a vector. X component is 1, y component is 2, z component is 3. Again, arbitrarily chosen. And we need, so the left hand side is given, we need to integrate these three equations. Okay, and we have to assume some initial condition. Let's assume that the initial conditions are all 0. So the TA has made a nice video of various ways to use different ways to in MATLAB to integrate. Okay, so there are routines which are available for integrating differential equations, and we can use those routines to solve this problem of integrating three nonlinear equations, three coupled nonlinear equations. And it looks like this. So theta 1, as if you plot as a function of time, it looks like this. It is constantly increasing. This is in radians and this is in time. Theta 2 goes like this. Theta 3 goes like this. So we know at any instant of time what is theta 1, theta 2 and theta 3. So let's say at t equals 2, we can find out these. And then we can find the rotation matrix corresponding to theta 1. Let's say this is something like 4 radians. I can go back and so x rotation is 1, 0, 0. First column is 0, 1, 0, 0. First row is 1, 0, 0. And then cos theta 1 minus sine theta 1, sine theta 1, cos theta 1. So these are those simple rotations which we had discussed last week. So I can find out the simple rotation about x, simple rotation about y, simple rotation about z. Okay, and then multiply the matrices in the order which you do, which is x, y and z, and then you can find the equivalent rotation matrix. And the equivalent rotation matrix has all the direction cosines. So basically it tells you how the moved coordinate system with respect to the original reference coordinate system. So we know what is the orientation of this rigid body with respect to the 0 coordinate system. So the moral of the story is that for orientation we have to solve a set of coupled nonlinear differential equations. These are ordinary differential equations, whereas in the case of position we just integrate separately each one of them. The x component integration, Vx will give you x, Vy will give you y, Vz will give you z. So in summary, the position vector of a point on a rigid body is a vector in 3D space. The linear velocity can be obtained by simply differentiating the position vector with respect to time. The orientation of a rigid body is represented by a 3×3 rotation matrix R, which contains all these direction cosines, Rij's. From here, we get two different forms of angular velocity vector. So one is a skew-symmetric matrix which is obtained as R dot R transpose. This is the angular velocity vector from this skew-symmetric matrix is called the space fixed angular velocity vector. This is independent of the choice of the body coordinate system, okay, and components along space fixed axis. We can also obtain a skew-symmetric matrix which is R transpose R dot, okay, and the angular velocity vector obtained from this skew-symmetric matrix is called the body fixed angular velocity vector. This is independent of the choice of the fixed coordinate system, okay, and components along body fixed axis. The angular velocity vector from these two are related by a rotation matrix, and we can also obtain the angular velocity vector in terms of Euler angles and Euler parameters if it is required. We can also estimate the position and orientation of a rigid body from the measurements of the angular velocity vector or the linear velocity. So basically by integration.